I'm Mikhail Derevyannykh and I'm from Eagle Dynamics. Today I want to present our new paper which is called Real-Time Path Guiding based on parametric mixture models. So what is the problem? If we try to render a frame using a regular path tracing algorithm, just relying on one sample per pixel, we meet our problem. We get high level of noise even with rendering the default responsive scene with two light bounces per path and one directional light emitter. We can afford more than 1-2 samples per pixel in real-time path tracing on modern GPUs, especially taking into account that we need to make other stuff in GPU too, like mesh animation, tone mapping, some camera effects, and so on. Even applying very popular SVG denoiser doesn't solve the problem completely. It could introduce bubbling, give biased, over-darkened results in some cases like that. This is the reason why we suggest to use the path guiding for sampling the first scattering direction, and as you can see, it really improves results. Moreover, it decreases the bias of the denoiser output. So this technique is our research. For solving the light transport equation, we usually apply Monte Carlo estimator for real-time application. But if we have a high variance estimator and limited samples budget, we get high level of noise. This is why it's common to apply important sampling technique from this integrand term. It usually leads to a decrease in the variance and consequently the noise level also drops. But usually in path tracing we apply important sampling only for BRDF term because we can simulate sampling from this distribution analytically most often. At the same time, incident lighter term can be deduced analytically before the start of the rendering process. Also, it's high dimensional function, and we need to have a way for combining it with BRDF term. We're inspired by work of Verba and Karlik and al. It's called Online Learning of Parametric Mixture Models for Light Transport Simulation. The authors suggested to use Gaussian mixture models for guiding path tracing algorithm. Some the important sampling inside lighting term using trained Gaussian mixture models, which they define in hemispherical space by some mapping. It's used to apply expectation maximization algorithm for optimizing parameters of mixture models. But authors deduced online versions of this algorithm, which will be pretty useful in our case too. In their case, they just iteratively train mixture models before the main rendering process. Also, it is important to notice that this technique caches mixture models in a set of points in virtual scenes. In the stage of applying path guiding algorithm, it just searches a set of nearest cache mixture models close to current heat sources location, and it tries to select best one candidate based on several heuristics. But because we have some interactive application with moving cameras, objects, and so on, this kind of structure could be hard to maintain. Also, it's pretty painful to implement efficiently an algorithm for searching closed mixture models. Load them to some temporal memory buffer and try to select the best one between them in GPU shader. So we believe that this technique is pretty good for offline rendering with static scene, but not for online rendering with dynamic scenes. This is the reason why we suggest to store all needed data per pixel in a frame buffer, constant speed of loading data, and fixed size memory usage. For supporting dynamic scenes, our algorithm just reproject data from old frame to a new one using motion vectors and some heuristics. Also, it's important to know that we have to transport distribution from hemispherical space of an old pixel surface to the space of a new one, just basic math. Moreover, for simplifying the problem of filtering and improving performance, we decided to use just one Gaussian loop, but include BRDF term inside our mixture model. From one point of view, It allowed us to achieve one sampling, multiple important sampling, where the first strategy is based on normal distribution, and the second strategy just regular BRDF analytical sampling. Compared to the work of Warburg, Karlik, and al., which also use multiple important sampling, our technique trains the probability of choosing a best strategy. And it's possible because we bind our mixture models to pixel surfaces. It won't be possible for world space storage type. Because we usually get just one sample per pixel in path tracing pass, we can just have one iteration of training mixture model per frame. But we suggest to represent second vertex of every light path as a virtual point light and store it to a temporal frame buffer per pixel in the end on the tracing pass, like in RestoreGI paper. After it, our technique just uses virtual point lights from neighboring pixels from some small window for accelerating training of mixture models. It can be useful for rapid training parameters of new visible pixels, for example, near the borders of moving camera. Or in some complex cases, we have low probability of sampling a light path with high contribution, and our technique helps to find these paths faster. Also, for guiding structures, become more responsive with less temporal lag because of it. Finally, our algorithm just consists of several steps. First, we run path tracing, which sampling a first scattering direction using a guiding mixture models from the first frame buffer. Secondly, we store result in virtual point lights to the second frame buffer per pixel. And finally, we sample neighboring virtual point lights for training Gaussian mixture models using online expectation maximization algorithm. That's it. We tested our algorithm in several popular scenes for real-time path tracing, like Bistro scene, Spanza, the regular one, and Specular, and also San Miguel scene. We achieved better results for uniform lighting, for some complex direction lighting, and for diffuse surfaces, and for specular ones also. Moreover, we want to notice that by introducing training adaptive weight in our mixture model, our algorithm doesn't decrease variance compared to the default important sampling in complex cases like this. This render confirms it. And also there is a result from Bistro scene that proves our statement. Because our technique decreases the noise level of renders, it helps achieve better results with the combination with SVGF denoiser. Pan guiding allows it to restore brightness, high frequency in directional shadows, and decreases the number of fireflies, which can be produced in cases with decreased value of control edge stopping function for luminance for achieving less blurring in final render and reconstructing some high frequency details like the shadows. Also, we try to capture the temporal stability level just by computing mean square error of SVGF output with the regular path tracing and with our technique. Regular one is blue line and our orange line. Our technique makes it really stable and decreases the error in several times. And also we benchmark our algorithm and um, usually it doesn't lead to any degradation of rendering time, but sometimes it slightly improves the overall performance level because using guiding mixture models make algorithm to generate more coherent paths. There is some small demo, disable guiding and turn on, more stability, disable, turn on, turn off. Now you can see that there is some lack of light on the floor, enabled guiding, reconstruct this lighting. helps to find these complex light paths. More stability. Turn off and you see over darkening. Turn on and everything is okay. Stable picture. Turn off and some bubbling and some small fireflies. And finally, pitfalls and future research. Using just one lob Gaussian may limit the effectiveness of path guiding. We need to research some ways of constructing mixture models based on several Gaussian lobs for real-time applications. Also, our solution decreases variance for estimating reflected light only from the first bounds because of relying on just screen space buffer, and this limits the effectiveness also. Moreover, biting mixture models with pixel surfaces better depth gives better results, but sometimes it introduces problems with surfaces with high variance of normals and enable jittering. And in cases of reprojecting data from old frames to new ones. Thank you for your attention.